In section 6.2, we're going to cover two more concepts of functions, those being one-to-one functions and inverse functions. So let's dive right in here and get to it. First is one-to-one functions. The cool thing about one-to-one functions is that a one-to-one function is exactly what you think it is. So there's two pictures of mappings here. These are both functions. If I were to ask you which is the one-to-one function, it probably wouldn't take you very long to guess that this top one is one-to-one, and that would be the correct answer. A one-to-one function means that, well, since it's a function, each input has only one output, so we only have one arrow coming off of each input value. But not only that, but if it's one-to-one, then each output also has only one arrow. So it's straight one-to-one. Here with those two arrows merging together, that's not one-to-one. So one-to-one function is exactly what you think it is. We have a more formal definition of that. I would say don't worry about it. It's a pretty simple concept, so you shouldn't have any trouble determining, in this case, whether this is one-to-one. And the answer is no. Right? This right here means that's not a one-to-one function. We have two inputs going to a single output. It is a function, okay? You'll notice if you just look at this left side, there's one arrow coming off of each input, but it's not one-to-one. Okay, if we have a set of ordered pairs, to determine if this is one-to-one, you can do a mapping. -2 goes to 6, -1 goes to 3, 0 goes to 2, 1 goes to 5, and 2 goes to 8. I would say that yes, that is one-to-one. Okay, pretty simple there. If we have a graph, we can use, there's a line test we can do. We do have, of course, the vertical line test that tells you whether a graph is a function. To tell if it's a one-to-one function, we have the horizontal line test. And so it works the same way. Here's two examples. Use the graph to determine if the function is one-to-one. And the horizontal line test says, okay, you look at the graph of your function, in this case x squared, we know that's like a U-shaped graph, right? And the horizontal line test says, if you can draw a line that crosses the graph more than once, in this case, I'm sorry, a horizontal line that crosses the graph more than once, then it's not one-to-one. So with this x squared graph, I can draw a line that crosses that more than once. I can draw a horizontal line that crosses more than once. So that's not one-to-one. For x cubed, if you'll recall the x cubed graph, looks something like this. In this case, we can draw a horizontal line across this thing, and it will never touch the graph. Well, in my case, it gets a little flat right there, but you know, if I'd drawn that a little bit more accurately, for that x cubed graph, it is one-to-one. That horizontal line is only going to touch once. So yes, that is one-to-one. So it's very similar to the vertical line test. Vertical line test says if you draw a vertical line that crosses more than once, it's not a function. Horizontal line test says if you draw a horizontal line that crosses more than once, it's not one-to-one. So that's it for one-to-one functions. Let's look now at inverse functions. The way an inverse function works, we have a definition here. And this only works when we do an inverse of a function. The requirement that we have is that in order for a function to have an inverse, it must be one-to-one. So that's this first point right here. Suppose you have some function f, it's a one-to-one function. Okay, well that means that for each x in the domain, there's exactly one y in the range, and vice versa. For each y, there's one x. Okay, that means it's one-to-one, right? That's what that means. And if we just make a correspondence from the range back to the domain, We call that the inverse of that f function. And to get a good idea of what that looks like, here is a function. Okay, this is a function. If we want the inverse of that function, notice that is 1 to 1. To get the inverse, you just switch. Notice here I have states on the left and populations on the right. If I just switch that around and put populations on the left and states on the right, switch all the arrows around so that the population is now the domain and the state is now the range, that's the inverse. Okay, so I started with this, states on the left mapped to populations on the right. Now I have populations on the left mapped to states on the right. That's the inverse. And that's basically how that works. The domain and the range are switching places. Okay. And we're not going to worry about stating the domains and range of the inverse functions. Don't believe that's required on the homework, so we'll not worry about it. So just in the same sense, when we just a second ago we said that x and y, or the domain and the range, switch places. If we have a set of ordered pairs and we want the inverse, all we got to do is switch each ordered pair around. So here it was -3, -27. When I do the inverse, it's now -27, -3. And I can just continue this process, switching the x's and the y's. Of course, some of these have repeated x and y values, okay, -1, -1, and so forth. So nothing changes on those, but there's my inverse function there. Just switched all the little ordered pairs around. If we were going to state the domain and range for the inverse, that's pretty clear that the domain of the inverse is just the x values of that new function. And then the range, of course, is the new y values. So there's that. And again, what we just said there, when the x and the y switch place, the domain and the range also switch place. So we do have this relationship where the domain of f is the range of the inverse function, and vice versa. The range of f is the domain of the inverse. So that does happen, and that can be useful if we're ever interested in finding the domain of and range of a one-to-one function. We'll not get into that. Just know that that situation does occur. Another way of thinking of an inverse function, if we start using equations, is to think of the inverse function as what undoes the original function. So just as a simple example, say f of x is 2x multiplying by 2. The inverse would be 1/2 x, where we divide x by 2, or we cut it in half. Okay, and since those are inverse functions, one undoes the other. That's really similar to, or the same as what we just saw in section 6.1. We had some problems where you did the composition f of g and g of f, and in both cases you got x, and that's because those were inverse functions. And so that's what we've got going on here with like 2x and 1/2 x. One undoes the other. If we do a composition, we just end up with x. So as an example, f of 3, remember f of x is multiplying by 2, so that's 2 times 3, which is 6. If we then take that 6 and do the inverse function, we cut it in half, we're back where we started at 3. And so, you know, we can do this sort of thing right here to show that those are inverses. You do the composition f inverse of f, and those just cancel each other out, and you're left with x. It's the exact same thing we did in that last section. And so that's what this says. We can verify that a function is an inverse by showing this composition both ways just gives you x. So let's do that for a couple of examples here. First, we have f of x is x cubed, g of x is the cube root of x. So to show that those are inverses, we're going to do the composition both ways. So f of g, that's f of the cube root of x, which is ends up being the cube root of x cubed, which if you cube a cube root, that cancels out and you just get x. So there's one way. Now we need to verify the other way as well. So g of f of x, that's g of x cubed, which means we're doing the cube root of x cubed, which of course is still just x. So that verifies what we needed to show. The composition both ways just gives us x. That means these are inverses. Part B, f is 2x plus 3, g is a half times x minus 3. And so looking at that here again, starting with f of g of x, that's f of a half times x minus 3, which is 2 times a half x minus 3 plus 3. So we're just taking this right here, plugging that into the x. When we work this down, starting with those 2's, they cancel out. And then, of course, the minus 3 and the plus 3 cancel out. We're just left with x, which is exactly what we needed to show. So let's do it the other way. G of f of x, that's going to be g of 2x plus 3, which is a half times 2x plus 3 minus 3. And again, we just work this down. Plus 3 minus 3 cancel. Everything just kind of unravels. Half of 2x, those 2's are going to cancel, and there's the x that we're left with. So that verifies those are inverses. And again, if you think about what one function does compared to the other, one undoes the other. When we plug an x value into f, it gets doubled and 3 is added. If you plug an x value into g, 3 is taken away and it's cut in half. So doubled plus 3 minus 3 cut in half. You see one undoes the other. And here's another example, this time with some fractions. So we're just going to do the same thing. F of g, that's f of 1 over x minus 1. So 1 over x minus 1. And actually, I think this actually is a typo. Let's make that a plus 1. Otherwise, things don't work out really well. So we're taking this right here, plugging it into that x. Okay. So what we get there, again, the plus 1 and the minus 1 are going to cancel. 1 over x, if we write that with a division symbol, it's a little more clear, I think, as to what's happening there. 1 divided by 1 over x is the same as 1 times that reciprocal, x over 1, which is just x. So that's what we needed, right? We wanted to show that that was an x there. So now let's do the other way. G of 1 over x minus 1. So now we're plugging this whole thing into this x. So we get 1 over x minus 1 plus 1. So make sure you get all those fractions in there. Again, just like over here, we had 1 over x. was basically just like a reciprocal twice. That's what this is. So this fraction is the same as x minus 1. And then, of course, minus 1 plus 1, we just get x. So that's that one. Again, showing that in both cases, we do get just a single x. So those are inverses. Okay.